Every year in the United States, hundreds of thousands of tons of sheet piles are driven into the ground. That's so much steel that it would be enough to build several aircraft carriers. Imagine, these metal giants don't rise up into the sea but disappear underground, holding our cities, dams, and ports from destruction. But how is a perfect steel profile, with a tolerance smaller than the thickness of a fingernail, born from a pile of old scrap? What happens in the furnaces with 3,000 degrees and on the rolling mills, where metal is formed at the speed of a car? Watch until the end, and you will discover the secrets of production that are usually hidden from prying eyes. Annually in the United States, hundreds of thousands of tons of these profiles are produced and driven into the ground. To imagine this weight, think of an aircraft carrier. One such ship weighs about 100,000 tons. This means that in a year, the country creates enough sheet piles to build several such steel floating cities. This is an endless stream of metal that goes underground to hold what is on the surface. It all begins, as in many stories about steel, at a huge scrap metal yard. This is a place where old ships, building structures, and industrial junk get a chance for a new, noble life. A giant crane with an electromagnet gathers tons of this metal and loads it into a huge ladle, which is sent to the melting shop. There, in the roaring hell of an electric arc furnace, where the temperature reaches 3,000 degrees Fahrenheit, this scrap is transformed into a boiling lake of liquid steel. Special alloying elements are added to this melt so that the future pile is not only strong, but also resistant to corrosion, as it will have to work for decades in moist soil. Next, this fiery river passes through a continuous casting machine, where it cools and solidifies, turning into a long, red-hot steel billet called a slab. This is our blank, our formless piece of dough, in which all future strength is already embedded. These hot slabs, cut into pieces of the required length, are sent to a reheating furnace. There, in a controlled heat, their temperature is again brought to the ideal plastic state, about 2,200 degrees Fahrenheit. They become soft and pliable, ready for the main transformation. And now the most interesting part begins: rolling. The red-hot slab comes out of the furnace and enters the rolling mill. It's necessary to form not just a symmetrical profile, but a complex shape with bends and, most importantly, with a perfect lock on the edges. The rolls of the rolling mill for sheet piles are not just cylinders. They are real sculptors of steel, having complex shaped grooves. The slab flies into the first pair of rolls with a roar, which squeezes it and begins to form the main profile, usually Z-shaped or U-shaped. Then it passes through the next pair, which further refines the shape. And so, step by step, passing through dozens of such rolls, our flat bar is transformed into a long, ribbed ribbon before our eyes. We talked about locks or interlocks. Well, the tolerance in their manufacture is only a few hundredths of an inch. That's less than the thickness of a fingernail. The red-hot steel ribbon flies along the rolling mill at the speed of a car, and at this moment, the rolls form a lock on it with such incredible precision. This is necessary because at the construction site, workers will have to connect hundreds of such piles. If the tolerance is even slightly larger, this giant industrial zipper simply won't close. On average, 1 square foot of a sheet pile wall weighs from 20 to 40 pounds. And now imagine one pile 60 feet long. Its weight can easily exceed 3,000 pounds. This is like the weight of a small sedan, concentrated in one long, thin piece of steel. And these piles, interlocked together, form a wall capable of withstanding the pressure of earth and water, equivalent to the weight of dozens of trucks pressing on it simultaneously. But the most important thing happens at the edges. The last sets of rolls, finishing rolls, form the most complex element of the pile, the lock or interlock. On one edge of the pile, a groove is formed, similar to clasped fingers, and on the other, a protrusion, similar to a thumb. These elements must be formed with an accuracy of a fraction of an inch. If the lock is too tight, it will be impossible to connect the piles at the construction site. If it is too loose, the wall will not be sealed and will leak water. Therefore, the rolls with incredible force, but at the same time with precision, press out this complex profile along the entire length of the red-hot steel ribbon, which can reach several hundred feet. The hot, perfectly formed pile crawls out of the last roll and along a roller conveyor goes to a cooling table. There, slowly cooling, it acquires its final strength. After cooling, it is checked for straightness and, if necessary, straightened on a special straightening machine. Then it's time for the final operations. A huge cold saw, with a deafening roar, cuts off piles of standard length from the long ribbon. Inspectors take special templates, or gauges, and carefully check the geometry of the locks. They check whether the fingers and groove fit perfectly, whether there are any defects that could prevent connection. This is a guarantee that, at the construction site, somewhere in a deep pit, these steel sheets will connect into a single, strong, and waterproof wall. Some piles may undergo additional processing. A special sealant is applied to their locks, which, when connected, fills microscopic gaps, making the wall completely sealed. The finished checked piles are collected into bundles, marked, and loaded onto railway platforms or barges by giant cranes. And so, these steel soldiers, born in fire and pressure, are ready to set off for their service, to go underground and silently, invisibly to all, bear the weight of the earth and the pressure of water, making the construction of the most daring modern projects possible. The lion's share of sheet piles is used in marine infrastructure, the construction of ports, piers, docks, and breakwaters. They are the silent guards of our coastlines. A huge number go to flood protection, forming the core of dams and levees along rivers, especially in places like New Orleans. And of course, they are indispensable in large cities, where a deep pit needs to be dug for the foundation of a skyscraper, right in the middle of dense development. This steel wall, driven into the ground, prevents neighboring buildings from sliding into the pit. So these hundreds of thousands of tons of steel are not just production statistics. They are a measure of our ability to tame the land and water, to build where it was previously impossible, and to protect our cities from the elements, one precise lock at a time. The finished piles lie in neat bundles, resembling giant packs of pencils. The first move is made by overhead cranes. A huge beam moves under the ceiling of the workshop. Powerful electromagnets or special traverses with several hooks hang from it. With a hum, the crane descends, and with a metallic clang, it picks up a whole bundle of piles, which can weigh 30 tons. The crane operator transports this cargo and carefully places it on a transport vehicle. And here we have two main paths, by land or by rail. If the construction site is relatively close, the piles will go by truck, but these are not ordinary semi-trucks. To transport 60-foot piles, special extendable platforms are needed. This is a very long trailer that can extend like a telescope, reaching an incredible length. Due to the length of the cargo, the driver needs incredible skill to navigate turns. Often, such cargoes are accompanied by special vehicles with flashing lights, which warn other drivers and help in difficult sections. Every turn at an intersection is a slow, calculated maneuver that requires all the available space. If the distance is long and the order volume is huge, the railway comes to the rescue. Bundles of piles are loaded onto long, flat car wagons. This is much more efficient for large batches. An entire freight train, loaded with hundreds of tons of steel piles, looks like the spine of some prehistoric beast. With a rhythmic clatter of wheels, it travels hundreds of miles, crossing states, to deliver its cargo to the station nearest the construction site. There, the piles are reloaded onto trucks for the final throw of a few miles. Every year, more than 12 million cars are scrapped worldwide, and this has become a massive industry running like clockwork. Imagine this. Your old ride could turn into a brand new skyscraper, and that worn-out engine might end up in a military battleship. But what actually happens to cars that have reached the end of the road? They are not simply tossed away. 90% of their materials get recycled. How are cars dismantled, crushed, and literally torn apart to be turned into something new? Today, we are taking a deep dive into this process. Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal. Unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle, but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns: oil leaks, gasoline spills, lead contamination — gasoline still contained lead back then — and other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, they are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Every single year, the world's oceans are left with hundreds of gigantic liners that used to be floating cities. Imagine this. Only one specialized shipyard in the country of India dismantles over 400 ships per year, and the utilization of just one cruise liner can yield up to about 44,000 short tons of steel. How does a vessel that once cost billions of dollars turn into a heap of scrap metal? Who makes money on this process? And why do the majority of ships finish their journey in southern Asia? Let us examine this process from the very first blueprint all the way to the very last cutting of the hull. Private yachts are produced all over the world, including in the United Kingdom, the Netherlands, Italy, and Turkey. But the major cruise liner production hubs are located in France, Germany, Italy, and Finland, where industry giants such as Chantier de l'Atlantique, Meyerwerft, and Fincantieri operate. Everything begins with the creation of a project, during which engineers and designers develop the overall structure, choose materials, and determine the technical specifications of the vessel. The design phase can last anywhere from 6 months to 5 years. Once it is approved, the shipyard begins manufacturing the main metal sections of the hull, which are later joined together in a massive dry dock or a specialized construction hangar. Construction starts with the production of large steel or aluminum sections that will form the hull. First, enormous sheets of metal are cut using laser or plasma cutting, and then they are joined by welding to create separate blocks. Each block can weigh anywhere from about 55 short tons to about 330 short tons, and their total number may reach into the hundreds, depending on the ship's size. After the welding is completed, the sections are painted with anti-corrosion coating and moved into a massive assembly dock, where the hull begins to take shape. The assembly process involves powerful cranes that lift the blocks and connect them to one another. Once the main structure is finished, the hull is reinforced with internal bulkheads, and initial communications are installed, including piping systems, ventilation ducts, and electrical cables. When the hull is fully assembled, it is launched into the water, and the fitting out of the interior begins. Partitions, electrical grids, heating and ventilation systems, air conditioning, and safety systems are put in place. At this stage, the ship gradually starts to look the way it will when it is completed. First, special soundproofing and thermal insulation materials are applied to the ship's metal hull, because the liner must be not only strong, but also comfortable. Next, metal frameworks are installed to serve as the foundation for the partitions and other structures. These frames are made of lightweight materials, such as aluminum or composite panels, to keep the vessel's overall weight lower. Thanks to modular technology, large sections of cabins and public areas are assembled at separate production facilities and then transported to the liner, where they are rapidly installed. Passenger cabins are usually manufactured as complete blocks, each including walls, flooring, plumbing, and furniture. These blocks are then transported to the ship and placed in their designated spots, after which they are connected to the ship's electrical network and water supply and ventilation systems. Larger liners can have more than 2,000 of these modules, and installing them can take several months. Public areas are much more complex, since each restaurant, theater, or lobby has its own design and intricate architectural solutions. For example, theater stages are equipped with moving platforms, sound systems, and lighting that is integrated into the ceiling. Swimming pools receive water purification systems, and sports courts are fitted with special non-slip surfaces designed to withstand wave movement. During the final stage, furniture, decorative panels, lighting, and finishing touches are installed. High-quality materials are used, ranging from exotic woods and marble to stained glass. Designers pay attention to every single detail in order to create an atmosphere of luxury and comfort. Once construction is complete, all systems undergo meticulous testing, including elevators, ventilation, safety features, and communication lines, so that the liner is fully prepared to welcome passengers. At the same time, powerful engines and control systems are installed on board. The main engines, which are typically diesel or hybrid, are mounted in the engine room before the liner's hull is completely enclosed. Each engine can weigh anywhere from about 22 short tons to about 55 short tons, and there may be between 3 and 6 engines depending on the ship's size. They are delivered to the shipyard dock by specialized cranes, then lowered through the engine room's top hatch and attached to vibration-damping mounts that reduce noise and vibration during operation. After the engines have been installed, drive shafts are added to transmit rotational motion to the propellers, Or, in the case of electric motors, they are connected to the power supply system. Most modern liners use azipod units, which are powerful electric motors capable of rotating around their own axis, giving the ship excellent maneuverability. All power units are connected to control systems located on the bridge and in the engine room. Once every technical system is in place, the liner is readied for its initial tests. First, static tests are conducted while the ship is still in the dock, checking how the engines function without leaving port. The power units are started up, and the electrical supply, fuel pumps, cooling systems, and emergency mechanisms are tested. Computerized control systems, which manage navigation, automatic speed adjustment, and ship stability, are also checked at this stage. Following these static tests, the liner is launched for sea trials, which last from about 2 weeks to about 6 weeks and include checking speed, maneuverability, and the operation of all systems under real-world conditions. The captain and technical personnel test how the vessel responds to commands, examining braking efficiency and the performance of the stabilization systems. The liner is taken into open waters, where the engines are tested at maximum power. Fuel consumption is measured, and noise and vibration levels in cabins and public areas are evaluated. In the final phase of testing, safety systems are examined by simulating emergency scenarios, testing firefighting systems, lifeboats, evacuation routes, and communication with shore-based services. Only after all tests are successfully completed is the liner formally handed over to the client, and it sets sail on its maiden voyage. But sooner or later, every liner heads out on its last voyage. Since no technology lasts forever, what happens to yachts and other vessels afterward? Are they actually utilized? And if so, how? According to data from the International Maritime Organization, around 1,000 seagoing vessels are utilized each year, of which about 200 are large cruise liners and passenger ships. Most of these vessels are dismantled in South Asian countries such as India, Bangladesh, and Pakistan, where the world's largest ship utilization shipyards are located. For instance, in the city of Alang in India, there is one of the biggest shipyards, which processes over 400 ships per year. First, the ship's owner assesses the condition of the liner and compiles a list of materials that can be recycled, sold, or require specialized disposal. The utilization of a single large cruise liner can produce up to about 44,000 short tons of steel, which after recycling is used in construction and other industries. In addition to metals, other materials such as wood, glass, and plastic are removed from the vessels for recycling or safe disposal. During this period, the ship heads to the specialized shipyard that handles the disassembly of ships. The largest of these facilities are located in India, Bangladesh, Turkey, and Pakistan. The liner or yacht makes its way to the site for utilization under its own power, or is towed if its engines are no longer functional. When the vessel arrives at the shipyard, the preparatory work begins. A team of engineers and environmental specialists evaluates the potential risks connected to hazardous substances, including fuel, lubricants, coolants, chemicals, asbestos, and lead. All of these materials must be carefully removed to prevent environmental contamination and to protect the workers' safety. In the first step, any remaining diesel fuel is pumped out of the tanks, which can amount to anywhere between about 10 short tons and about 55 short tons, depending on the size of the vessel. Next, the pipelines, oil filters, and engine cooling systems are cleaned to remove all residual lubricants and chemicals. Specialists also deal with air conditioning and firefighting systems, which might contain harmful gases like freon. After that, the ship is disconnected from all power. The electrical networks are shut down, and the batteries containing toxic substances are removed. In the engine room, the generators are dismantled. They can be resold or used on other ships. During this period, specialists also check for hazardous materials, such as asbestos, which was once used for pipe and wall insulation. Asbestos is carefully taken out, sealed, and delivered to specialized facilities for safe disposal. The next step involves removing all equipment and items that might be reused or sold. Furniture, lighting fixtures, plumbing, doors, decorative panels, carpets, and even kitchen appliances are dismantled from the liner. Many of these items are sold on the secondary market or used on other vessels and in hotels. The following stage is dismantling. First, the ship is secured in a dry dock or pulled onto a specially designated beach, which is common in South Asian countries such as India or Bangladesh. This stabilization is necessary to keep the hull steady during cutting because losing balance could cause an accident. Next, the upper structures are gradually taken apart, including the top decks, bridge, funnels, and other external components. These sections are typically removed in large pieces using cranes. Workers start dismantling the upper structures and decks, steadily moving down toward the main hull. Metal parts like steel and aluminum are cut into smaller segments, and the separated materials are sorted and prepared for subsequent recycling. For example, steel is melted down to create new products, while non-ferrous metals such as copper and aluminum are put to use in various industries. When the upper structures have been fully removed, the main hull is cut apart. Several methods can be used, depending on the thickness of the steel and where the ship is located. The most widespread method is gas cutting, where specialized torches heat the metal to over 1,500 degrees Celsius, which is about 2,732 degrees Fahrenheit, and then the steel is sliced by a stream of oxygen. For thicker steel sections, which can be up to about 8 inches thick, plasma cutting or hydraulic shears may be used. Cutting of the hull begins from the top and proceeds downward so that the structure does not collapse under its own weight. Huge steel blocks, weighing anywhere from about 55 short tons to about 110 short tons, are separated and moved to specialized areas where they are further broken down for recycling. On average, the hull of one large cruise liner can yield from about 33,000 short tons to about 44,000 short tons of steel, which is later reused in construction and shipbuilding. Special attention is paid to cutting the underwater part of the hull, since it is the sturdiest section and contains ballast tanks that might hold residual water. Underwater welding and cutting techniques are employed if part of the hull remains in the water at that stage. In the final phase of dismantling, the last remains of the keel and bottom are cut into fragments, which are loaded onto trucks or barges for transport to metallurgical plants. Utilization of cruise liners and yachts can last from a few months to more than 1 year, depending on the vessel's size and construction. Completing the dismantling process signifies that the ship officially ceases to exist. All materials suitable for reuse are sent for recycling, and everything else that cannot be repurposed is disposed of in accordance with environmental regulations. It is important to note that the utilization process must meet international environmental standards. Organizations such as the International Maritime Organization develop guidelines and standards for the environmentally sound utilization of ships, known as the Hong Kong International Convention for the Safe and Environmentally Sound Recycling of Ships. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress, so there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES II ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. What do rockets and a fabric stronger than steel yet lighter than plastic have in common? And how do engineers create technology that withstands 17 million pounds of thrust, the freezing cold of space, and temperatures in the thousands of degrees? Today, we'll uncover the secrets behind rocket construction, from revolutionary materials to million-dollar final tests. Get ready, this journey will leave you in awe. First off, a rocket isn't just a metal cylinder with engines, as it might seem at first glance. Turns out, many of its components are made of advanced materials called supermaterials. Take carbon fibers, for instance. They're incredible. Imagine a fabric that's lighter than plastic, but stronger than steel. These fibers are woven into thin layers, almost like a carpet, then infused with special resins and baked. This process creates the rocket's body, capable of withstanding extreme stress. Picture this. In just 1 square inch of carbon fiber, there can be up to 50,000 individual fibers. Each one is only a few micrometers thick. That's thinner than a human hair. Let's dive deeper. Carbon fibers are made from a polymer called polyacrylonitrile, or from carbon residue in petroleum. The process begins with long, thin threads of this polymer. These threads are heated to extraordinarily high temperatures, up to 5,500 degrees Fahrenheit. During this process, organic components are removed, leaving nearly pure carbon composed of tiny yet incredibly strong crystals. These crystals in carbon fibers are aligned in one direction, like perfectly arranged bricks in a wall. This alignment gives the fibers extraordinary tensile strength. Plus, they're highly heat resistant, making them perfect for the harsh conditions of space, where temperatures can swing by hundreds of thousands of degrees in either direction. For rockets like the Falcon 9 from SpaceX, carbon fibers are often combined with epoxy resin to create composite materials. These composites are used for fuel tanks, bodies, and even protective shells, anything that needs to be strong yet lightweight. Carbon fibers are produced in specialized factories, most of which are located in Japan, the United States, and Europe. Companies like Toray Industries and Hexcel are leaders in this field. From these factories, the fibers are shipped to facilities where rockets are built. The weaving of carbon fibers happens on specialized machines called automatic winding machines or robotic braiding systems. At the center of the process is a massive mold shaped like a cylinder or cone, which becomes the rocket's body. Fibers are carefully wound around this mold. The winding isn't random, it's precisely calculated. Layers of fibers are laid at different angles to ensure maximum strength and resistance to stress. It's similar to making plywood, multiple layers with different grain orientations, but on a nanotechnology level. This research took me a long time, and I pieced together this video frame by frame over several weeks to show you. I hope you enjoy it. Now, let's see what happens next. After the body is woven, it's time for the resin. Resin is evenly applied to the fibers to create a strong composite. Think of it as gluing layers of paper together, except instead of paper, you have carbon fibers, and instead of glue, you have specialized polymer resins. Once the body is ready, it goes into a massive oven called an autoclave. Here, at about 400 degrees Fahrenheit and under high pressure, the resin hardens into an ultra-strong material. This step is critical because, without it, the body couldn't withstand the enormous stresses and temperatures during a rocket launch. This process typically happens in specialized hangars or production facilities. For example, SpaceX's Gigafactory, enormous, immaculately clean spaces. Robots and automated systems control everything to ensure not a single speck of dust interferes with creating the perfect rocket body. The size of the machines and molds is staggering. Imagine a cylinder tens of feet long and several feet in diameter. Access to these top-secret facilities is required to witness this incredible machinery in action. They say it's a sight that's out of this world. As you might guess, I couldn't see everything with my own eyes. The completed SpaceX Falcon Heavy rocket is 230 feet of pure engineering brilliance. It weighs over 3 million pounds, that's the weight of about 7 blue whales, and can lift 140,000 pounds of cargo into orbit, more than a fully loaded Boeing 737 with passengers, fuel, and luggage. Titanium and aluminum alloys are the foundation for many rocket components that require a combination of lightness, strength, and resistance to extreme temperatures. Fuel tanks must withstand immense pressure and temperature changes since they store cryogenic liquids. Aluminum lithium alloys, which are lightweight yet incredibly strong, are often used for this purpose. Turbopumps frequently use titanium. It's not only strong, but also highly corrosion resistant, which is crucial since these components constantly interact with aggressive substances like rocket fuel. The rocket's frame, as well as various mounts and connectors, are often made from aluminum alloys to reduce the rocket's overall weight. But when additional strength is needed, or components face extreme loads, titanium is the go-to material. Some engine parts, such as combustion chambers or structural components, can also be made from titanium alloys. They handle high temperatures and vibrations during engine operation with ease. For reusable rockets like the Falcon 9, titanium is used for legs and parts that ensure reliable landings. For example, the famous titanium grid fins of the Falcon 9 allow the rocket to adjust its trajectory during re-entry. In short, these metals are like the skeleton and muscles of the rocket. One provides lightness, the other unparalleled strength. Next, we were taken to a workshop where every inch seemed to breathe technology. Honestly, I initially thought I had stepped onto a sci-fi movie set. Robotic arms, lasers, and 3D printers creating components from metal powder, all working together like a symphony. These 3D printers are a game changer. Instead of cutting components from blocks of metal, they build them layer by layer. What's fascinating is that this not only saves time, but also allows for shapes that were previously impossible to create. For example, internal parts of fuel pumps are now printed as complex grids, making them lighter and more efficient. And now, the most exciting part, final assembly. Rockets are assembled step by step, the lower stage, middle, and upper stage. Every segment is inspected and tested for proper fitting. Engines are a story of their own. They're installed last, like crown jewels. And these engines, they're engineering marvels. They generate incredible thrust while operating with the precision of a Swiss watch. Each rocket comprises over 100,000 individual components. Every single one must work flawlessly, because even the smallest mistake can turn a billion-dollar project into a pile of scrap metal. Some rocket components are assembled in rooms cleaner than hospital operating theaters. For instance, satellites or optical instruments are built in clean rooms where air is filtered to remove even the tiniest particles of dust. The staff wears protective suits because even a single speck of dust could damage the electronics or optics meant to function in outer space. Once assembly is complete, the rocket undergoes a series of tests. Picture a massive platform where the rocket is secured and ignited at minimal power. Engineers check everything, from tank pressure to engine behavior. One of the most fascinating steps is simulation. Special chambers recreate space conditions: vacuum, low temperatures, and radiation. The rocket must prove it's ready for any challenge. Each rocket launch can cost up to $100 million, roughly the price of 50 Ferraris for just one moment in space. Impressive, isn't it? The sound wave from a rocket launch is so powerful, it can destroy not just buildings, but the rocket itself. That's why facilities like NASA or SpaceX conduct acoustic tests. Rockets or individual components are placed in special chambers where massive speakers and water cooling systems create a sound that mimics a launch. This ensures the rocket's parts won't break under the immense sound pressure. Acoustic tests are mind-blowing. Imagine a sound exceeding 160 decibels. For context, human pain starts at 120 decibels. These powerful speakers literally bombard the rocket with sound to check if its components can withstand the pressure. Finally, after months or even years of work, launch day arrives. Standing in front of a massive monitor, I felt the world come to a halt. The countdown, the roar of the engines, the clouds of smoke, and the rocket rises into the sky, leaving a fiery trail behind. This is the moment when every bolt, every detail, and the efforts of hundreds of people come together. When a rocket launches, its engines generate over 17 million pounds of thrust, enough to lift an entire island or power a small town for an hour. Before a rocket launch, tons of water are poured under the launch pad. And no, it's not to put out fires, it's to reduce sound pressure. Without this, the acoustic wave from the launch would be so strong it could damage the rocket within seconds of liftoff. When I first set foot in this facility, I had no idea how much work and innovation goes into every launch. But now, sharing all this with you, I'm even more in awe of what human imagination can achieve. Rockets are a true symbol of how far we can go when we set ambitious goals. Imagine every tire on your car as the result of decades of innovation, research, and fine-tuned manufacturing. Goodyear, one of the giants in this industry, produces tires that are engineering marvels. But how exactly are these technological masterpieces made? Let's break it down, step by step, and get a sense of the scale of this incredible work. Goodyear was founded back in 1898 and named after Charles Goodyear, the inventor of vulcanized rubber. The production of Goodyear tires begins with carefully selected raw materials. The key ingredient, of course, is rubber. But not just any rubber you'd find in a forest. This is a complex material made from natural rubber and synthetic substitutes. Natural rubber is harvested from the sap of hevea trees grown in tropical regions. This sap is called latex, a familiar term, right? The main suppliers of natural rubber are countries in Southeast Asia, like Thailand, Indonesia, Vietnam, and Malaysia. To collect the sap, neat cuts are made on the bark of hevea trees, similar to how maple syrup is gathered. Latex slowly oozes out and is collected in small containers attached to the tree trunk. A single tree produces only a small amount of latex daily, so plantations are packed with thousands of trees. Initially, latex has a liquid consistency and needs processing. Acids are added to it, causing the latex to coagulate into an elastic mass. Typically, formic acid is used. Yes, formic acid. Sounds surprising, doesn't it? The name dates back to the 1700s, when scientists first extracted this acid from ants. Back then, chemists boiled ants and discovered a liquid with peculiar properties. It turned out to be an acid that many insects, including ants and bees, use as a natural defense mechanism. Today, no one harvests formic acid from ants anymore. Instead, it's synthesized on an industrial scale from chemicals like methanol or carbon monoxide using modern technology. This method is way more efficient than collecting it from insects. Formic acid works perfectly for latex processing because it's non-toxic in small amounts. It easily coagulates the protein molecules in latex, turning the liquid into a solid elastic mass. Plus, it dissolves in water, making it easy to wash away any residue after treatment. After adding the acid, the resulting material is pressed into blocks or rolls and dried. This process significantly reduces its volume for easier transportation. The dried rubber is shipped to factories worldwide. For Goodyear, this includes plants in the United States, Germany, China, and other countries. The rubber is transported by sea in large bales that are easy to store and use in tire production. This covers natural rubber, but how do they make the synthetic kind for tires? Synthetic rubber is an artificially created material made from petroleum products. Its main component is butadiene, a chemical derived from gases left over after refining oil or natural gas. Butadiene, along with other chemicals like styrene, undergoes a process called polymerization. This chemical reaction links molecules into long chains, creating a material with high elasticity. The most common types of synthetic rubber are styrene butadiene rubber and polybutadiene rubber. To give synthetic rubber the properties needed for tires, such as strength, wear resistance, and temperature resilience, special additives are mixed in, like carbon black or silica, and plasticizers. Synthetic rubber is produced on a large industrial scale and shipped to factories in the form of granules, rolls, or preformed blocks. At Goodyear's factories, a rubber compound is created by combining the best qualities of both natural and synthetic rubbers. The rubbers are weighed precisely according to formulas tailored to specific tire models. In massive industrial mixers, the rubbers are blended with other ingredients: carbon black, silica, sulfur, oils, and chemical additives. Think of it like making dough, but under high pressure and heat. During mixing, the rubber turns into a thick black paste. This stage is crucial because it defines the tire's future characteristics: grip, durability, and temperature resistance. The mixture is repeatedly needed to ensure all components are evenly distributed. This guarantees uniformity in the final rubber. After mixing, the material is cooled and formed into large sheets, which are then cut into pieces for further tire production. The process of cutting rubber sheets at the factory is truly impressive in scale. This isn't done with kitchen knives, but with massive industrial machines that work with the precision of jewelers, but on a factory-wide scale. The thickness of the rubber sheets varies depending on the part of the tire they're meant for. For example, the layers for the tread are thicker than those for the sidewalls. Before cutting, each roll or sheet passes through an automated inspection system. Machines check for defects like air bubbles, tears, or uneven thickness. Anything that doesn't meet standards is immediately discarded. Cutting is done using specialized high-tech machines. Rotary knives, resembling spinning discs, effortlessly slice through the rubber, creating perfectly straight strips. Lasers, the most advanced technology, can cut rubber without physical contact, ensuring extraordinary precision. The laser beam literally melts the material at the desired spot, leaving a flawlessly smooth edge. Depending on the production stage, sheets may be cut into long, narrow strips for tire reinforcement, or left in large pieces for the tread. Everything is programmed, and parameters are automatically adjusted based on the type of tire being made. After cutting, materials are sorted by type and size. Strips are rolled up, and sheets are stacked. All of this is transported to the next department for tire assembly. Each machine processes thousands of feet of rubber daily. Powerful engines roar, knives spin at incredible speeds, and workers monitor everything through computers. This conveyor never stops, producing hundreds of tires every hour. It's like surgery on an industrial scale. Everything must be flawlessly precise to ensure the finished tire is safe and high quality. Goodyear is one of the world's leading tire manufacturers, with production facilities in 22 countries and 52 factories. Let's circle back to another fascinating aspect of this story: the ingredients beyond rubber. Why are they added? Carbon black gives the tire strength and protection against UV rays. Silica improves road grip, especially in wet conditions. Sulfur and other chemicals help rubber retain its shape and elasticity under different conditions. As you can see, every detail matters. But that's not all. Let me tell you about the skeleton of the tire. You know it's not just rubber, right? The core consists of a multi-layered structure. The quality of this framework determines the tire's strength, durability, and ability to support the weight of the vehicle. This process involves several sequential and high-tech operations. But first, let's look at the materials. Textile cords are a must in the tire's construction. These are threads made of polyester, nylon, or even aramid, a highly durable synthetic fiber. They provide flexibility and lightness. Steel cords are also added. These are thin yet incredibly strong metal wires that give the framework rigidity and the ability to withstand heavy loads. Rubber acts as the bonding material between the layers of cord, creating a strong yet elastic structure. Cords pass through specialized machines that evenly coat them with rubber. This binds the fibers together, protects the textile or metal from moisture and corrosion, and ensures a strong bond with other rubber layers during vulcanization. This process is incredibly precise. If the rubber layer is too thick or too thin, it could compromise the tire's safety. Next comes the breaker. This part of the framework lies between the tread and the tire's core. Its job is to distribute the load across the tire and protect it from punctures. The breaker is made of multiple layers of steel cord laid at specific angles. Each layer is cut to a template and laid out in a precise sequence on specialized drums. The angles are computer-controlled to achieve the desired characteristics. The main framework is assembled on a special building drum that rotates, allowing all layers to be evenly laid out. First, textile layers are added for flexibility. Then, metal wire rings are added to form rigid sidewalls. These rings help the tire stay firmly on the rim. The tire bead, its inner edge that contacts the wheel, must be extremely strong. The bead ring is made from multi-layered steel strips coated in rubber. Side layers of rubber are added to the main framework to protect the tire from damage. This entire sandwich is secured on the drum using pressure and heat.